So I'm going to go through in this video and talk about logarithms, specifically evaluating them, simplifying them, finding their inverses, and then graphing both the logarithm and then also the inverse. So to begin with, if we are asked to rewrite a logarithmic equation in exponential form, what we're going to do, for example, if we're given this logarithm, remember for a logarithm it would be, in this case, 7 raised to the third equals 343. So it's kind of like a circle. So it's the base 7 raised to the third equals 343. So that's how we would rewrite it. For the second example, it would be 64 raised to the 0 equals 1. Okay. In contrast, if we were asked to rewrite the exponential equation in logarithmic form, this is a little bit more tricky, but we can still do it. Remember, 50 is your base, okay, so it would be log base 50. And then since it's raised to the half, that's what's going to be on the equal sign on the other side. And then it's going to be 5 root 2. So it would end up being log base 50 of 5 root 2 equals 1/2. And if you do the reverse of that, right, put it back into exponential form, you'll see that that matches up. Okay, so here are some key properties of logs that we're going to be using throughout this lesson. So the first one is that if you have log base, anything, any base, doesn't matter what it is, 1, that's going to be equal to 0. And the reason why is something raised to the 0 power will always be 1. The next one's also really important. Anything log base b of b equals 1 as well, because b, whatever number it might be, 10 or e or whatever, raised to the first power equals that value. Okay. The next one is the one that we're going to be using pretty extensively, and that's the fact that log base b of n equals n, because if you look at this, b raised to the n equals b to the n. So this is something that we're going to be using when we are simplifying. So for example, if I have log base 2 of 2 to the n, I can figure out that that would just be n. If instead I have log base 2 of 4 to the n, I want to get that 4 in, I want to figure out a way to make that equal to 2 so that I can just solve and get n. And it'll make more sense once we actually look at a practice problem. So the next one's one we're going to use pretty extensively. Log base b of b to the n equals n. And I'll show how that looks in a second. But for example, if b, let's say for example, were 2, that would be saying 2 to the n equals 2 to the n. So it makes sense, but we'll actually see it numerically in a second. And then finally, we've got ln of e to the n equals n, because remember, ln means log base e. So that's pretty much the exact same thing as what we just saw with the previous log base b of n equals n. And then finally, the last two, if I take my base, b, and raise it to the log base b of n, that will just give me n. And so to understand this a little bit more clearly, I just took the log of this, so I took it out of exponential form and put it into log form. So it's b raised to the log base b of n equals n. So if I undo this by using the log base b of n equals log base b of n, showing that, then that actually makes sense. So that's a key equation. And the other one is e raised to the ln of n equals n. So let's look at these and actually apply them, because it doesn't mean much unless you can actually utilize them. So the first example here, just as a quick reminder, if I give you just log x, it's implied that your base is 10. So let's look at an example. So I have log of 1,000,000. Okay, so there are two different ways that I can do this. I'm going to show you both of them. Okay, but in order to answer this question, I'm going to be using that property of logs. So log base b of b to the n equals n. So I'll show you how I'm going to use it right now. So there are two ways to do it. First way is you can undo this log. So remember, it would be log base 10 of 1,000,000. So I could say 10 raised to the what equals 1,000,000. So that's what I have on my left-hand side here. 10 raised to the what equals 1,000,000. That's one way to do it. Or what I can do is I can use this property of logs that I gave you and say, okay, I want my bases to be the same. I want the same b. So since I know it's log base 10, how can I make 1,000,000 have that same base, that base of 10? Well, 1,000,000 is just 10 raised to the 6th. Okay? And so the reason why this second one on the right-hand side is valuable is once I figure out that relationship and can set it up like this where I have the same base, I now know my answer is just n, which in this case is 6. Or I could do it the other way and say 10 raised to the what is 1,000,000, and you get the answer of 6. But when it gets a little bit more complicated, the one on the right, honestly, I like both of them. So it's totally up to you how you do it. Another function is the fact, or another property is the fact that when you have ln of x, what that means is you have log base e of x. Okay, so let's look at an example with this. So if I have ln of e to the 5th, there are two ways I can write this. I can recognize the fact that this is log base e of e to the 5th and say, okay, so that means it's going to be e raised to the what equals e to the 5th, right, which is what I have on my left-hand side, so obviously the answer would be 5. Or I can make sure that I have the same base. So since this is ln of e to the 5, I know it's log base e of e to the 5th. So based on my property of logs, then the answer would just be 5. Okay, let's look at some more examples. So for example 1, I gave you log base 3 of 1/27th. So I'm going to show you the two different ways I did it. The first I'm going to do it the log way. The other way I'm going to do it with my question mark. So the first way is I recognize, okay, I want 1/27 to become 3. 3 raised to the whatever. But I want to have the same base so that I can find my answer. So what I do is I recognize the fact that 1/27th is the same thing as 1/3 cubed. Okay? Then I'm going to get rid of this 1 over by simply making it 3 raised to the negative third, right? Because that would switch it into my numerator just by making my exponent negative. Now, if you notice, my bases are both 3, therefore my answer is -3 when I simplify this. Or you could do it the other way and say 3 raised to the what equals 1/27th. Okay? And so 3 raised to the what equals 1/3 cubed, and so I would recognize that that's -3. You can do it either way. For number 2, I'm going to first do it my log way. So I'm going to say log base of 1/4, log base 1/4 of, well, I want my base here, I want my 16 to become my base, the 1/4. So how do I make 16 1/4? Well, I recognize first the fact that 16 is 4 squared. Okay? Then remember I want the base 1/4. So I'm going to make this, the 4 squared, I'm going to make it 1/4 by simply making it a negative to the -2 versus just squared. Okay? So now my base is the same. Okay? So what I can do is say 1/4, 1/4, so therefore my n is going to be -2. So again, my whole goal is for my base to be the same, right? So I can get the same b so that then my n will just be my simplified answer, so -2. You can do it that way, or you could say 1/4 raised to the what equals 16. Well, if I want to simplify this, right, 16 is 4 squared. So if I made this 1/4, so 1/4 to the -2, that would give me my answer as well. Or you could just recognize that 1/4 raised to the -2 is 16. Okay, so honestly, either way works perfectly fine. So what I want you to do right now, you've got 4 practice problems. I want you to pause this and I want you to evaluate them. All right, so here are my solutions. So for the first one, I still did it both ways. I prefer the log version just because it makes more sense to me, but whichever version works. So I recognize that my base is 5, so I need to make 625 equal to 5. So what I do to have that base of 5. So 625 is 5 to the 4th. So now I have 5s there. Therefore, I know that my when I evaluate this, it's going to be 4, right? Because that's my n. Or you could say 5 raised to the what equals 625, and the answer is 4. Okay. Number 2, 216. I want it to have I want it to be 6, right? The base of 6. So it's going to be 6 to the 3rd. And so when I simplify this, it's going to be 3. Or you could say 6 raised to the what equals 216, and you get 3 as an answer as well. All right, 3 is a little bit more complicated, so hold on, you can do it. Keep in mind your base is 16, so I want 1/4 to be 16. So how do I do that? Well, I recognize the fact that 16 raised to the 1/2 is 4. Okay, so then I have 1/4 here, but I want the 16 to be in the numerator. I don't want it to be in the denominator. So if I just raise this 1/2 to the negative, this would become 16 raised to the -1/2. That is 1/4. Fantastic. My bases are the same now, so therefore when I evaluate this, my answer is -1/2. Or you could say 16 raised to the what is 1/4. Well, 16 is 4 squared. and that equals 4 to the negative first, and therefore 2 times whatever I'm trying to figure out, my question mark, that equals -1. So my answer would be -1/2. You can do it either way. Okay? For 4, I've got this problem. Okay? Keep in mind, to make my 343 equal to 7, it needs to be 7 raised to the third. So my answer is 3. Or you could say 7 raised to the what is 343. So of all of these questions, 3 is definitely the more challenging one. So I would definitely go back and try problems like that. So 3 is challenging. And then I also did it in example 2. Those are the 2 real challenging ones here. Okay? So for these problems, what you need to do is you need to simplify the expression. Okay? So make sure that you're using your properties of logs and simplify. And then for the last 4 questions here, I ask you to find the inverse. So remember, to find the inverse, you need to simply switch your y and your x, and then you need to isolate your y so that it becomes y equals again. Okay? So pause the video, do these problems, and then come back and I will explain them. So here are my answers for them. Okay? So if you notice for number 5, remember your rule that b raised to the log b of n, that just equals n. So if you notice, your base here is 30 for both of those, so your answer will just be 4. For number 6, we're going to be using the property that we had been using before, which is log base b of n equals n. So remember, there are 2 different ways to do this. I'm going to first do it the log way. So my base is 6, so I'm going to take 36, make it 6 by making it 6 squared. So that becomes 6 to the 2x. So my answer here, when I simplify this, will just be 2x. Or you could say 6 raised to the what equals 36 raised to the x. Okay? Well, 6 to the question mark, we don't know, equals, well, I want to have the same base in order to set them equal. So I'm going to make it 6 to the 2x so that I have 6's as my bases, and so my answer is 2x as well. Okay? I really prefer the log way of doing it, just to clear the air. For the next one, I've got 125, so I want that to be 5. I want a base of 5, so I'm going to take 5 to the third is 125. Okay? And then that would become log base 5 of 5 raised to the 3x, because remember, when you raise 5 to the third by x, you end up multiplying your exponents. So your simplified version of this, your simplified solution, would just be 3x. Or you could say 5 raised to the what equals 125. Well, 125 is 5 cubed, so your answer would be 3x as well. 8 is just like number 5, where your answer would just be your n, which is x. Here for the inverse, remember, you're going to switch your x and your y. So I switched my x and y here. Now in order to get y by itself, I need to take the log of 7 of x, and that equals my y. So if we undid this, remember, this is 7 raised to the y equals x, and so that's exactly what I have here. So your inverse would just be y equals log base 7 of x. For 10, again, I'm going to switch my x and my y, but here, now instead, I'm going to take 1/2, raise it to the x, that will equal my y. So my answer here is y equals 1/2 raised to the x. For the next one, I switch my x and my y. Be careful here, because in order to take the log of this, I need to move my 3 over, so I added 3. Now this is going to be 2, log base 2 of x plus 3, make sure to put that in parentheses, that equals my y. Okay, so this was when we were practicing taking it from exponential to logarithmic form. This is why we were doing it, in order to be able to do this. So this would be the inverse of that equation. Finally, if I have y equals 6 plus log x, I'm going to switch my y and my x. Make sure to move your 6 over, so it's x minus 6 equals log of 10 to the y, 10 of y. And the reason why I put the 10, the base 10 there, keep in mind log of y is log base 10 of y. And the reason why I need to do that is because now, in order to isolate y, I need to say 10 raised to the x minus 6 equals my y. And so that would be the inverse of that. Okay? All right, next we're going to work on graphing logarithms. So here's the first example. I give you this log, okay? And I want you to graph the inverse. So the first thing I need to do is I need to substitute in my x and my y. So I substitute my x for my y. Again, just like what we did before. To isolate y, I need to do 2 raised to the x equals y plus 3. and then I'm going to subtract by 3. So my inverse equation is going to be 2 to the x minus 3. So for my log graph, okay, my vertical asymptote represents the value that x cannot be equal to. Okay, so if you think about it, you cannot, if you look at this log equation, log base 2 of x plus 3, the value within that log cannot be 0 because 2 raised to the there's nothing that you can raise 2 to in order to get 0. So your vertical asymptote would be x equals negative 3. The domain is going to be that it has to be greater than negative 3 because remember, 2 raised to the nothing would give you a value less than or equal to 0, and your range would be all real numbers. And so if I were to ask you to find the X Intercept, which represents the value of x for which your y equals 0, I'm going to plug in 0 for my y. So remember, it's going to be 2 raised to the 0 equals my x plus 3. So when I solve this, because 2 to the 0 is 1, I get negative 2. So my x-intercept is going to be negative 2, 0. So that's for my log graph. Now let's find it for my inverse. So instead of a vertical asymptote, just like what you were doing before when you were working with exponential graphs, you're going to have a horizontal asymptote. So the horizontal asymptote now is going to be looking at the 2x minus 3 is going to be the value that your y will never reach. Well, since 2 to the x cannot ever be 0, that means that my y will never become negative 3. So my horizontal asymptote is negative 3 since 2 to the x cannot be 0. My range here is going to be y is greater than negative 3. My domain is going to be all real numbers. And since my x-intercept is negative 2, 0, since this is the inverse, my y-intercept is going to be 0, negative 2. It works out quite nicely. So if I graph this, if you look at this, notice the blue was for my log, the red was for my exponential form. And these are inverses, and I especially know that they are inverses because if I plot y equals x, so you see that black dotted line there, these will reflect, they are symmetrical over that y equals x line. You can fold it over on each other. Okay, so that's how I know that they are inverses of each other. All right, second example. Keep in mind that the value 2x minus 1, that value in there, that cannot equal 0, which means my vertical asymptote is going to be x equals 1/2. My x-intercept is going to be the value of x for which y is going to be 0. So when I actually plug that in, I get 39,063. So let's see how that works. So if I make my y equal to 0, okay, what I'm going to do is I'm going to move over, I'm going to add 7, okay, to both sides, and then I'm going to do 5 raised to the 7th equals 2x minus 1. When I solve for x, right, I can scoot over the plus 1, divide by 2, and I get 39,063. So that is my x-intercept, the value of x at which y would be 0. Okay? My domain here is going to be that x has to be greater than 1/2, and my range is going to be all real numbers. If I find the inverse of this, so if I plot this, remember I'm going to switch my x and my y, okay? 5, so I'm going to scoop my 7 over, then I'm going to do 5 raised to the x plus 7, that equals 2y minus 1. And then I'm going to isolate my y by adding 1 to both sides, and then I end up getting my inverse equation, 5 to the x plus 7 plus 1 divided by 2. Okay? So if I were to find my horizontal asymptote here, okay, keep in mind your horizontal asymptote is the value for y that y cannot be equal to. So keep in mind 5 to the x plus 7 cannot be 0. There's no way for that to be 0. Therefore, my horizontal asymptote is going to be 1/2 because if 5 to the x plus 7 cannot be 0, right? 0 is that horizontal asymptote, but then it's going to be plus 1 divided by 2. My horizontal asymptote is 1/2. My y-intercept here is going to be simply 0, 39,063 because I got that from the log. You can also just plug in 0 to your equation and you'll get the same value. So to graph, again, so this confirms your vertical asymptote of 1/2, your horizontal asymptote of 1/2, and then notice how they are symmetrical over the y equals x line. Okay, so here are 2 problems for you to do. Pause the video. You need to graph the regular function stating the domain, range, vertical and horizontal asymptote. And then you need to do the exact same thing for the inverse for both of these problems. Okay, so here are my answers for you. Okay, I'm just going to go through pretty quickly. My vertical asymptote here is the value for which x cannot be equal to, which is 0, because you can't find, when you have log base 3 of a value, it cannot be 0 or less. Your domain is that it has to be greater than 0. Range is all reals. For my y-intercept, remember you plug in 0 for your y, which I did, and you solve that. You can follow my work, and you end up getting with 1 over 81, 0. For your inverse, remember you plug in y for your x and x for your y, and then I've got to isolate my y again, so I subtracted 4. 3 raised to the x minus 4 is my inverse equation. So my horizontal asymptote there, remember what value can y never be equal to for this problem? That would be 0, because 3 to the x minus 4, there's no way for that to be equal to 0 or less than 0. My domain is all reals, and my range is that it has to be greater than 0. And my y-intercept, remember, you just flip. So it's going to be 0, 1 over 81. Or you could plug in 0 into your equation, and 3 to the negative 4th is 1 over 81. For 14, it's a lot of the same thing, right? What value for x can this not equal? Well, since you can't have log of base 6 of 0, x equals 4. Your domain is that it has to be greater than 4, and your range is all real numbers. Your x-intercept, I plugged in 0 for my y, and I solved it. You can see all of my work there. So you end up getting 4 plus 136, or just 4 and 136. Okay? And then if I were to do the exact same thing with the reverse, I plug in x and y again, I flip them, and then I solve for my y. I get y equals 6 to the x minus 2 plus 4. My horizontal asymptote, remember, since 6 to the x minus 2 cannot equal 0, my horizontal asymptote is y equals 4. My domain is all reals, and my range is that it has to be greater than 4. And again, my y-intercept now is going to simply be the flip of what the x-intercept was for the inverse. So 0, 4 to the 136, or you can just plug in 0 for x, and you'll get that same answer. Notice for both of these graphs, they are mirror images of each other over the y equals x line, so that's a nice way of checking yourself to make sure you got the correct inverse.